So first off, good morning. I'm very excited to be here. I just want to say thanks to the organizers and the program committee for giving us the opportunity to talk about something that's slightly different and more on the networking side of the house, which is where I am. So I usually give this presentation with Daniel, and he was supposed to be here, but he has some travel issues. He has a complicated passport. But the good thing is that that's why we have redundancy. Daniel and myself are in a team called Network Foundation, and our team is very much focused at looking at how different parts of the Facebook network fit together. This is because, as you can imagine, the network is global and it's very large and it's divided into specific areas and specific teams, and we want to make sure that the overall performance and the overall reliability of the network is what we expect. So this means that we do a lot of performance, a lot of monitoring sort of investigations and initiatives. And to talk a little bit about what problem this system is trying to solve, we first need to get some context. And this is a small representation of what a typical data center network looks these days, at least in our type of environment and some very large enterprises. And this is a representation that's actually very scaled down. And essentially what you can see here is, and I don't know if the laser is visible, I think it is. If you see this from left to right, what you have is essentially two hosts, two servers, right? And you have a top of the rack, which is pretty common, and then you have like the network that interconnects these two servers, which, as I said, this is a topology that's called CLOS, and it's actually pretty old. It comes from telephony. It's like from the 70s that sort of the networking space has taken over the last, let's say, 10 to 5 years, and has made popular again for a number of reasons that I'll touch on as we go. And so essentially you have like this aggregation layer, which here is 4 devices, but in reality this can be much larger. Then you have, this is usually called like a leaf. This is the spine layer, which here it has 6 devices, and then maybe this middle layer is a layer that interconnects a couple of buildings or a couple of data halls. Depends of your infrastructure, right? But as the sort of takeaway of this is that there's many potential paths that your data between host 1 and host 2 can actually take, right? And that's the crux of this issue. Which this topology is great. This topology allows a number of things, has a number of benefits. It allows us to have smaller platforms, which reduces the blast radius. But you need to live with the fact that between those two hosts you might have a very large number of potential paths, right? And this is where FFS comes in, which, as you can imagine, this is a system that exists in Facebook production. And what we wanted to do, because I'm really not a fan of this sort of presentations where we are just saying, hey, we have this solution and there's really nothing to show for. We wanted, because we can't really open source the production system because it's built and it's intertwined with a bunch of whole Facebook internals. We wanted to create essentially a proof of concept, a sample system that would allow people to explore this problem in their environments, in their own networks, because every network is different. So what is FFS trying to solve? As I like to call it, it's essentially trying to find the needle in the cloth. So we have this topology that I mentioned before. Let's say that maybe the person or the service owner that owns these two hosts, let's say that this is, for example, database, and they're telling you something like, we have this database replication, and it's been running, an order of magnitude more than what it usually takes. And, we have checked our service, we have checked our metrics, and, it's the network. So, tell me why the network is doing this, very bad, very evil network. And now as an on-call, or as a group, because sometimes these adventures essentially pull the on-call and everyone around them. You have to sort of figure out in this maze of devices and links and complexity, which, again, I want to emphasize that this representation is just a representation that's easy to show on Keynote. On the actual day-to-day, there's no way of showing this in a graphical way, or there is, but essentially it just all mushes together as dots and links because there's so many devices. You now need to figure out where's the problem, where's the needle, right? And this happens, especially at scale, this happens more often than not. And what usually happens in these sorts of scenarios is that we need to isolate what device has a problem so we can take an action, right? And the typical network monitoring strategy here is, people would go and look at what we lovingly call passive monitoring. So this is monitoring that's based on what the device gives us, what counters, instrumentation, telemetry we can get out of those devices, and then this gets fed into the monitoring pipeline to try to give us, hey, who's lying, right? Like who has a problem, right? So in these type of scenarios, you do this investigation and doesn't really reveal anything, which sort of makes sense because at least in our environments, like the common failure modes, the common problems are very automated at this point. So if we had signal that one of these devices had a problem, like that device would get taken out of service automatically, or a human would get a task ticket saying, hey, like the automation has failed to take action here because the audits say this is not safe. So human, please make a judgment call, or the automation failed in a new fun way. Which in this case you might not have this signal. And why you might not have this signal? I have examples that go from very simple and very mundane to very exotic and mystical. So a real example, a couple of years ago, we have this exact same situation. I mean, I don't think it was a database replication. It was some internal service saying, hey, like I do this operation, I have this graph, this should take, this should take this amount of time, and it's ballooning out of control, and like I'm getting lag, et cetera, et cetera. You guys figure it out, it's you. And so we do this investigation, and we can't find what it is, or we do this very manual, very tedious investigation, and eventually we narrow it down to the dude that's right there. And we say, okay, this device is bad. We have no idea why, because when you ask him, hey, how are you? He's like, I'm amazing. It's like, I'm the greatest I've ever been. And we are like, yeah, but you are like mangling packets like there's no tomorrow. You are like eating all my packets. So we take the device out of service, and service owner is super happy. Well, he's not super happy, but like he's happier than before. Now he doesn't have the problem anymore. But we are now left with a device that like we don't know why it's failing. Like if we put traffic back onto the device, which we do, to kind of say, okay, like is this a coincidence? Is this a real thing? Like we see the exact same things. Packets get mangled, sadness ensues. This was a few years ago, so most of these devices were external vendor devices. So we engage the vendor, and we say, hey, vendor, we have this situation. We explain the story, right? They're always shocked. It's great. They're always like, this is completely impossible. And we tell them, like, no, it's possible. And then they go, like, can you give me, like, a packet capture that shows the packet getting mangled? And we are like, like, if the packet enters your device and it's never to be seen again, how do you want me to give you that? And they're like, I don't know. But anyway, like, after a while we convince them, like, yeah, this is a real issue, and like, we report this enough that like they trust us. So then we have the conversation, and like, they look at all the basic stuff, which we had already done, and like, like I said, I have faith that our normal monitoring pipeline would pick this type of thing. And we get to a point where we're like talking directly to the ASIC, and we are dumping like hexadecimal counters and all that fun stuff, and we're like translated from like things that no human should ever have to read into like something that we can interpret. And at some point, someone says, but like, because at this point we had already narrowed this down to like the port, right? Like, hey, when traffic goes through this port, sadness. And we start looking at the hexadecimal stuff, and we say, hey, like there's a bunch of like symbol errors here, right? And someone is like, symbol errors. This is like normal CRC errors. Like these are the errors that you get when like the fiber is dirty or something like that, right? This happens all the time, everywhere. I mean, I'm sure it's happening now. And like I'm sure now automation is taking something out of service because it's happening somewhere in the network. And we go, well, like, how is this possible? Like we would have caught this like 3 minutes after it started, right? And then we go look at we are looking at hexadecimal counters. So we go look at the normal counters, and the normal counters are all saying 0, right? So we go, okay, so like if we don't get the counters, yeah, we're never going to catch this. And then, we tell this to the vendor, and the vendor goes, let me investigate. And essentially what they come back with is that they have like this middle layer that takes the hexadecimal counters and, surfaces them to like the normal counters, and that process is, not happy. And with the process not happy, like it times out, and when it times out, the counters just stay at 0. And that's a very mundane example of this. So like, like after they got all they needed, we rebooted the device, and like this lighted up like like massively, and we just did like normal troubleshooting, and then this went away. And like I said, this is a very mundane example. I have much more exotic, much more mystical examples, right? So this is what we want to do. Like passive monitoring is not enough. Like we have a percentage of time where we're going to have cases similar to this, and we need to be able to identify this without like spending a week like we did in that sort of simple example of multiple people time and the vendor to kind of identify this very, essentially what it was, a bug in their implementation of in instrumentation, right? So this is where like this system kicks in. Essentially, this is a way of doing active probing, right? And the idea of this active probing is like we're going to dynamically map the network, and we're going to inject synthetic traffic over the paths that we have previously mapped to try to make sure that when we have a device or an interface that's essentially causing these issues, we can identify them and take them out of service as fast as possible. So when we said, okay, let's try to replicate, like a smaller proof of concept, a sample system of what we have in prod, like what were our needs? What did we want to do? We wanted to have traffic similar to production. And what I mean here is this type of solutions, at least active probing in networking, tends to be very ICMP based. The problem is that real customer traffic is not ICMP, and this can lead to a number of things, especially in this type of very wide ECMP topologies, right? Which is the second point. We wanted this to be ECMP ready. If we have, let's say, 100 paths between host 1 and host 2, but we are only exercising 20%, then yeah, like if anything happens on that other 80%, we're going to be blind, right? We want this to be independent of devices, which I guess this point is somewhat apparent after what I've described. Devices fail and lie and misreport things on a number of occasions, so we wanted this to be as independent as possible. And there's different degrees of independence that you can have in active monitoring. Depends on the approach you're taking. And we wanted this to be precise enough for automation. Ideally, the goal of these systems is to provide some signal that you can action at 3 in the morning by a script and not have to page someone. Because when you don't have this, what usually happens is that sort of like database example that I mentioned. Like the database folks or service owners in general will get paged because their metrics like will tank. And then they will do some investigation. They will say, okay, this is not me. And then they will page the on-call person. And then the on-call person will do some investigation. And each step just adds time to resolution. So even if even if the signal is not 100% accurate, we want this is preferable to essentially hours of this impact, right? So what are the building blocks of this proof of concept? I mean, again, we were trying to make this as simple as possible because this is, like a tool to explore these problems, not necessarily something that you can. We weren't trying to do something that you could just put in production and call it a day. And the first block of this is how do you trace the network? And this is, these paths are dynamic, and these paths will change because of maintenances, because of failures, because of routing policies. You want to be able to do this dynamically, right? The second component is the traffic generation. So after you understand how the network is mapped, how many different paths, unique paths do you have between two hosts, then how do we generate traffic there to actually test the quality of those different paths? And those are done with open source tools, and most of the stuff is done with open source tools. And the part that we actually wrote a little bit is the sort of the glue that holds all of this together, which is essentially the concept of the master, which is receiving all the inputs from the pingers and running an algorithm to provide that estimation of where do we think the problem exists, and do the coordination of how many pingers, how many pongers do I have, right? Which the architecture is, essentially you can have these 3 roles. You can have this master node, you can have a pinger or a ponger, and they can do different combinations of these roles. And all of this is using web services, so there are things there that are pretty common, and there's nothing very mysterious there. Flask, Celery, Postgre. And essentially what the master is doing, and I'm going to talk about the workflow in a second, but the master is doing all of that coordination. Is who do you register against when you come up as a pinger or a ponger. So the master has a centralized view of everything that is available to run these tests, and he sort of acts like the master of puppets there. And like the pingers and the pongers is exactly what you would expect. The pingers and the pongers also synchronize because you need to understand the path, both going in the direction of the ponger and what's going to be the reverse path that that traffic is going to take, because more often than not, that might not be symmetrical. Depends on what layer of the network you are, but it's also a common thing. And like for tracing, we're using doubling traceroute, and for the traffic generation, we're using iPerf, which are open source, well-known tools. So what's the workflow, or like how does the workflow look like? So again, this is simplified. This is what we have sort of put for people in GitHub that you can use to kind of reference and kind of get started with this. But essentially, the idea is, as you have, like if you were going to deploy this in a fleet of servers, you would deploy this with, something like Chef, for example, and part of that deployment would be who do they need to register against. We are doing this sort of concept of having the pingers and the pongers registers because this provides freshness sort of information for the master. And what I mean by this is like this allows the ability to not have a static, like if one of those servers crashes or if you take a server down for maintenance, like this allows some pretty good fresh information for the master to know and to have when you're going to do tests. You don't want to be doing tests against stale targets, right? So when you want to start the actual analysis or the actual test, which, here I'm going to do it on demand at the end, but you could essentially, like our production version is running this all the time because this gives you a baseline of what's normal and what's abnormal. But essentially, again, like, each network is different and like you're going to have different tolerance for how much bandwidth you can use for this type of tests or how much resources on the servers you can be using for this type of tests. But essentially, when you decide, hey, the test needs to run, what you're going to have is that the master is going to communicate with the available pingers, and then it's going to give me, hey, this is your target list. Go run this and report back, right? Which, in case you're wondering how often that takes, also is all very customizable. I think like what we have in the lab is that we're in 50 trace routes. I think it's for a minute, and then the iPerf is for a minute. But you can tweak this depending on the size of the network and depending on what makes sense. So when this happens and the pinger says, okay, I need to hit all these pongers, they talk to each other, they synchronize, because like I said, we also need to get the reverse path here. And essentially, we do what it's called a UDP link quality test. And we decided to use UDP because it was pretty flexible. The issues that we face on the network are, like happen in a very similar way when the packets are UDP. UDP also is pretty resilient to polarization, so it's a good fit. And essentially, after all of that's done, the pinger will send those results in essentially JSON back to the master. And then the master is going to run the algorithm and is going to give you an estimation out of the network that you mapped out, the information that you provided. This is where I think the loss of a situation exists, right? So, the demo. We have this topology, and there's an interesting thing about this. I usually do this live, but all of this is running on real hardware. And this is running on real hardware because when we were developing this, like one of the, essentially one of the interesting thing or one of the requirements that we had is that, hey, we need to have a lot of ECMP here. We need to have all these different potential paths, right? Virtualized environments do not do ECMP very well. I actually spend more time trying to get virtualized, network topologies to do ECMP properly than actually like validating that doubling traceroute or iPerf of like the sanity of the results that we were getting, simply because since ECMP is something that's done usually on hardware, depending on the implementation of the hardware that you're using, this is not very, very well virtualized, right? And it doesn't really have like a lot of support, so we were running into all sorts of mystical and exotic issues. So this is running into actual hardware in a lab that we have in Spain, but that lab has a terrible, terrible VPN. So I was trying it yesterday, and like it was super slow. So I'm just going to show you a recording of this running and like the different logs. And what we're going to do is we have a script that generates loss in that link. And essentially how that's happening is because all of this is real hardware, we have this very small script that we specify an interface, in this case, that interface that's connecting core 1 and spine 3, and this is putting an access list. So this is adding and removing an access list constantly, and every time the access list is there, some traffic is getting dropped by the device. It's similar to what would happen if you had CRC errors or anything of that sort. And we have 3 hosts. We have these 3 machines. We have this sort of aggregation layer, and we have a spine layer and a core layer, right? So there's a lot of path diversity that you can go from between hosts. So let's take a look at the actual demo. And this is a view from a web service in the master. And we did this, again, the whole idea of this was to, we didn't want to be reading the logs and trying to follow along in the logs. So we just created this very simplistic, UI that when I took this video, network was not properly spelled there. That gives you an overview, right? So this is from the point of view of this host, which is the master, telling you, hey, I have all of these folks registered. Right? So this is, machine 2, machine 1, machine 3. And, in here, everyone is a ponger and everyone is a pinger. So you kind of have that full mesh story. And, essentially, this gives you a very quick overview. This is also the perspective of a pinger because he's also a pinger. You can see there that, we have this configured to do 50 trace routes. And, he's obviously not going to ping himself. So, he was pinging host 3 and host 2. So now when I kick this off, it triggers that workflow that I was talking about, which is from step 2. And these are the logs from PC2. We're going to be looking at this from PC2. And the first step, and I don't know if that's readable, but I will do some enhanced zooms. And this essentially, hey, I need to start doubling trace route, and I'm going to start against machine 2 and machine 1, right? And this will kick off the first step of this, which is let's map the network. And not the volume I want to change. This doesn't have any sound. I'm the sound. And these are the parameters that we start off, the source port, destination port. And this is because the path that you choose is selected by this tuple, and that tuple is composed of source IP, desk IP, source port, desk port, right? So this will take a while, and what we're trying to determine here is essentially how many unique paths do I have between 2 hosts, right? Because again, it doesn't really make sense for me to do 50 link tests if I only have 4 different paths, right? So at this point, iPerf has started, which means we have determined how many unique paths we have between the 2 hosts, and I kick off the ACL script. And here you can sort of see, but this is in a JSON format, and I'll show the JSON now. That gives you this information. It's very easy to understand, very easy to read, and you can see it here, right? And this is hey, from my perspective as a pinger, I know that for this source port, this destination port, I have this unique path, and then this unique path, and all the different unique paths that I have between myself and my targets, right? And this is the information that I'm going to use with iPerf in order to generate that sort of link quality test. Because I want to exercise, if I know, hey, if I use this combination of source port, desk port, all of that, I go through this set of links, I'm going to send an iPerf with the exact same parameters, and it's going to get hashed over the same exact route. And this is one of the real hardware that's running on that, that's running this story. And if you take a look at this, let's do better zoom. If you take a look at this, you can see how we're injecting the sort of ACLs, and when that ACL is injected, we're going to be dropping some traffic. That's our sadness in the network simulator, right? And this is essentially the script that's essentially adding and removing this over the period of the test, right? There are fancier things. There are some utilities that you can do, increase latency, but for our use cases, this was more than enough. And that's the, if you remember from the diagram, that's the link that's connecting core 1 and spine 3, that 131 network, right? And you can go back to the web UI, and the web UI is hey, I know I need to get 3 pinger results. I haven't really received them. like this is like the JSON backend that web is built with, which has all the information. As you know, like we were doing this for like our sanity, and we just said, okay, this is pretty easy to put in a UI, so we don't have to be just like refreshing the JSON to get a readout. And it says, hey, I'm like step 3 out of 5. Like I know this is 70%. I'm running iPerf. So again, this is pretty explanatory. So when iPerf is done, I'm going to compile all my results for the different paths, and I'm going to send that back to the master, right? And like iPerf is still running at this point. Some of them have finished, and again, I'm going to show the JSON in a second, but you have the different details there, and this essentially gives you what you care about, which is like, for this particular path, what is my loss profile, right? Like, what was the performance of that particular path? Which, like this could be extended to also, maybe you don't have loss, but maybe you have a path that like performs less for whatever reason. Maybe you have like a mismatch in like speeds, right? And I'm going to show what I mean in just a second, right? So if we take a look here, this is what actually gets sent back to the master. And if we like take a look, let me do more enhanced zoom, like CSI. You just have, my target here is host 3, and I send this with this source, with this destination. This is the path that this is going to take. This is for how long, this is how many bytes I sent, like this is the actual speed of the network, and this is the loss that I got back, right? And if you look down, this is for that same target with going over a different path, and I have no loss. So you can also use this to calculate, hey, maybe you don't have loss, but maybe you have different like performance of the network, and why. We're not doing it here, but it's definitely a possibility because the information is there. And all of this is going to get sent back to the master, and then the master is going to run the algorithm to establish the estimation of where do we think we have that particular loss. And that's described on GitHub if you care about like what the algorithm is actually doing. But again, like it's nothing fancy. The idea of this was to provide more proof of concept for people to explore this problem than anything else. So at this point, like in the UI, we can see, hey, like the status of this is finished, and this should be problematic circuits, but the 131 is the one that has the highest probability of being, it's the top talker here is the one that like we believe has the actual issue, right? Which, like if you wanted to implement this as an actual solution, maybe you would take that and then you would generate an alarm and you could have another system take action. Another thing we did is we have like this automatic like view of the network and the loss, which results usually in a graph that's really hard to comprehend by humans. And this is with our demo topology that wasn't that big, right? I mean, this video is like a couple of months old, so like the more recent version has a better graph, but the idea is the same, right? Like this represents like the different potential paths that you have between different hosts in a topology that's not even as big as the original one that I showed. And yeah, like I said, this has been open source for a while. This is on Facebook Experimental FFS, and it should have some documentation. And like we try to be pretty responsive. So if you have any issues, or like you try to deploy this and it doesn't make sense, or you need any help, feel free to comment, and we'll reply, or feel free to ping me directly. And yeah, that's it. Thank you very much.
We've got a lot of time for Q&A. If anyone has any questions, you can just step up to the mic.
We also have a booth, so if you want to chat with me in the breaks or in the booth, that's perfectly fine.
Thank you, Jose.
Thank you.